This video is a super speedy recap of the thermodynamics topic in AQA A-level chemistry. I've explained things very quickly and without practice questions, so if you do need more detail or some practice for yourself, be sure to check out the videos in the full playlist. But if you want one last-minute cram before your end-of-topic test or your final A-level exams, then this is the video for you. Thermodynamics is the science of heat. Often within thermodynamics, we'll be discussing enthalpy changes, which are changes to heat energy happening at constant pressure. Often these will be standard enthalpies, in which we're either making 1 mole of a substance or using up 1 mole of a substance. Some of these enthalpy changes, such as enthalpy of formation, are measured under standard conditions, and we tend to assume that the pressure is 100 kilopascals, and if the temperature isn't explicitly given, we assume 298 Kelvin. We start with two definitions that you learned in Year 12, but that are still necessary here. Standard enthalpy of formation is the enthalpy change or heat energy change at constant pressure when 1 mole of a compound is made out of its constituent elements. Those are just the elements that are included in that compound, under standard conditions, so 100 kilopascals and 298 Kelvin, with all reactants and products being in their standard states. Remember, you need to say all reactants and all products, not just everything. We can represent this with a chemical symbol equation like this. Note we're making 1 mole of water, and water is a liquid, whereas oxygen and hydrogen are gases. As we saw in the energetics topic, both delta HF and delta FH are normal credit-worthy ways of denoting this. Then standard enthalpy of combustion is the enthalpy change or heat energy change when 1 mole of a substance is completely burned in oxygen, or you might say burned in excess oxygen, with all reactants and products being in their standard states. Here we don't say under standard conditions because this is combustion, so it's not standard conditions. The temperature is going to be much higher. Standard enthalpy of atomization is the enthalpy change when we make 1 mole of gaseous atoms from an element in its standard state. There are two different ways that this can happen. If we're thinking about a metal, then all we're going to be looking at is a state change from a mole of solid atoms to a mole of gaseous atoms. But if we have a molecular substance, then that molecule needs to break apart. And this is where people start to get a little bit confused, because you need to remember that atomization will make 1 mole of gaseous atoms. It doesn't matter how many moles of molecules we start with. So in order to make 1 mole of gaseous atoms, you're going to start with half a mole or a quarter of a mole or an eighth of a mole of the molecule. You met first ionization enthalpy in Year 12 as part of mass spec, so you know that this is the standard enthalpy change when a mole of gaseous atoms loses an electron each to form a mole of gaseous ions. Remember, it doesn't matter what type of ion an atom would usually make in a chemical reaction. Here we're always removing that first electron. After the first ionization energy come the second and third and fourth, and in each instance we're just removing 1 electron and increasing the charge by 1. First electron affinity is measured when electrons are added onto gaseous atoms or negative ions. Just like with ionization energies, we don't have 1 electron affinity, we have subsequent ones if an atom is able to receive more than 1 electron. The first electron affinity of a non-metal is going to be exothermic, while the second or third will be endothermic, because we're adding an electron onto something that is already negatively charged, and that negative ion is going to repel the new electron that's being added. The lattice enthalpies of formation and dissociation are inverse processes of each other. So the exothermic process of lattice formation is the direct inverse of the endothermic process, and so the two enthalpy values will be the same magnitude but with different signs. Lattice formation is the standard enthalpy change when 1 mole of solid ionic compound is formed from its gaseous ions, and this is often what we're trying to work out when we construct Born-Haber cycles. To write an equation, I need all of the relevant ions in a gaseous state joining together to make 1 mole of ionic solid. You should be aware that the most exothermic lattice formations occur for small, highly charged ions, as these have a higher charge density. When you discuss the values for lattice formation, be sure to say more or less negative or more or less exothermic. Don't say bigger or smaller, as this is ambiguous when dealing with negative numbers. Students are often confused by enthalpies of hydration and solution because they do sound very similar. The enthalpy change of hydration is when water molecules surround 1 mole of gaseous ions, and this is going to apply to a specific element, so you need separate values for each element in the compound. We use AQ for water because this isn't water that's taking part in a chemical reaction, it's just making the ions aqueous. The standard enthalpy of solution is that much more realistic everyday process where 1 mole of an ionic solute is dissolved completely in enough water that the ions are no longer interacting with each other. And this is going to be one value for the compound rather than each element independently. Mean bond enthalpy is the heat energy required to break 1 mole of covalent bonds, and it's averaged across a range of molecules. Hess's law tells us that the enthalpy change or heat energy change at constant pressure for a reaction is independent of the route taken, and Hess's cycles allow us to make predictions about enthalpies that are difficult to measure directly. The Born-Haber cycle is a really specific version of a Hess cycle, and it's applied to an ionic solid. It allows us to calculate the lattice enthalpy of formation by using ionization energy, electron affinity, enthalpy of atomization, and enthalpy of formation. Born-Haber cycles allow us to predict the enthalpies of formation for theoretical compounds that don't exist yet, and it allows us to predict whether these compounds will be stable and actually likely to exist in the real world. To construct our Born-Haber cycle, we start by taking the elements in their standard states, and this will be the second rung of the Born-Haber ladder. Any exothermic processes in this diagram with negative enthalpies are represented by arrows going down, and endothermic processes with positive enthalpies are going to be represented by arrows pointing up. So firstly, we're going to make our ionic compound. This is standard enthalpy of formation, which is delta HF. It's an exothermic process, so that arrow points down. Next, I need to turn both elements into gaseous atoms, and it doesn't matter which order I do these in, but I tend to always go metal first. So there's my standard enthalpy of atomization for magnesium, and then the next one tends to be the first point that things go wrong, because people forget that standard enthalpy of atomization is to make 1 mole of atoms, and here we're making 2. So my value will be double the value listed in the data table. Then I need to think about gaining and losing electrons in order to form ions. So we start with the first ionization enthalpy of magnesium. Don't forget to include the electron. Don't just have your single positively charged ion and no electron. Everything needs to still balance. And then we're also going to remove a second electron from each magnesium ion in order to produce these magnesium 2+ ions. Now, each electron that has been produced can then be given to a chlorine atom to make a chloride ion. So this is going to be our first electron affinity. And what we need to remember here is that this is going to be an exothermic process, so the arrow is pointing down, and also that we're doing it twice because we have 2 moles of chlorine atoms. So again here we need to be doubling. And then finally, our mole of gaseous ions of magnesium and our 2 moles of gaseous chloride ions can join together to form a mole of our solid ionic compound, and this is the enthalpy of lattice formation. The next step is to look through the data table and assign a value to each one of these arrows. Whether it's a really simple Hess cycle question or a more involved Born-Haber cycle, I like to write start and end at either end of the arrow that I'm trying to figure out the value for, and then link them up, because this is just a really quick and easy way to make sure that in the stress of the exam you don't accidentally go the wrong way around the cycle. So each time that I'm going the wrong way up an arrow, I'm going to take the negative of that number. So I'm going to end up with the negative of 2 lots of -349, the negative of +1450, the negative of +736, the negative of 2 lots of 122, the negative of +150, and then this final arrow I'm going the correct way down, so I'm just going to add it on, and that's going to give me an overall value of -2524 kilojoules per mole. In part 2 of the thermodynamics topic, we encounter the concept of Gibbs free energy and the calculation which refers to enthalpy, temperature, and entropy. Entropy is a measure of how random or disordered a system is, and everything is always tending towards greater entropy. So the only way that we can avoid that is if we're putting in work or energy. Now, all entropy values are greater than 0, they're all positive, but an entropy change can be negative. As a general rule of thumb, if a chemical reaction leads to an increase in the number of particles, this increases entropy and gives us a positive entropy change. And an example of this would be the chelate effect, which we see in the transition metal topic. Likewise, a state change where we have a gas rather than a solid, or a chemical reaction which produces gaseous products, is going to lead to an increase in entropy. Every chemical has a value of entropy, and we can use these to calculate the entropy change of a reaction where we subtract the reactants from the products. So for instance here we start off thinking that water is 189 and there are 2 moles of water, so we would double that to give us a total of 378, and then hydrogen is 130, so 2 moles of that would be 260, and then we add on the 205 for oxygen, so that gives us 465, and then 378 take away 465 gives us an entropy change of minus 87. So we're getting less entropy because actually this is becoming more organised. It's important when we put these values back into the Gibbs free energy equation that we bear in mind that entropy is calculated in joules per mole per Kelvin, but delta G and delta H are in kilojoules per mole. So you need to convert your entropy data before you can use it in this equation. A typical Gibbs free energy equation is likely to ask you whether a reaction is feasible. So feasible reactions favour the formation of products under the conditions where the reaction is actually happening. They're not all fast and they're not all exothermic, but Gibbs free energy is a value that we can calculate to predict whether that reaction is spontaneous or not. And when we say free energy, we mean energy that is available to do work as opposed to energy that's stored and locked up somehow. When delta G is less than 0, the reaction is feasible. When it's greater than 0, it's not feasible. And crucially, the point at which it's exactly 0 is when it becomes feasible. So we're going to use this a lot in our calculations. Lots of Gibbs free energy questions will ask you to work out the temperature range where the reaction is feasible, and this might be phrased as a standalone question where you have to do all the work, or they might break it down into asking you to work out the entropy change and maybe even giving you some mean bond enthalpy data so you can work out the enthalpy change. But regardless of how the question is set up, the crucial thing we're looking for is where does the reaction become feasible, which is the point at which delta G is 0. And this is important because at that point, delta H is equal to T delta S. So we work out entropy in exactly the same way as we did before, bearing in mind that we're then going to have to take that value and convert it into kilojoules per mole per Kelvin, so divide by 1000, and then we can plug this into our question. So we're saying we're looking for the point at which minus 822 is equal to minus 0.2715 multiplied by T, which is the temperature in Kelvin. And if I solve that, then I'm going to get an answer of 3068, and I can say that this reaction is going to be feasible all the way up to that temperature. Finally, it's important to remember that while Gibbs free energy tells you about the feasibility of a reaction, it doesn't tell you anything about its rate. So for instance, graphite is thermodynamically unstable. It will break down, but it's kinetically stable, and therefore that process takes a very, very long time. Thank you very much for watching, and I hope you're now feeling a bit more clued up about the A-level thermodynamics topic. Good luck for your exams, and if you have found this video useful, don't forget to like and subscribe for more A-level chemistry content coming soon.